So thank you very much, Igor and Pavel, for the invitation. I'm very happy to be here. I'm going to present a joint work with Tamas Kalman and Alex Postnikov. All right, and this is about the Tutte polynomial. So the Tutte polynomial is a well-known graph invariant. And here in this work, the motivation was to extend that invariant from the setting of graphs to the setting of hypergraphs. So there had been some attempts in the past at doing that, but that were somewhat unsatisfactory. So we were looking for the right definition. And when we finally found it, we could move on, and we discovered one more thing, which is that this polynomial invariant for hypergraphs, it behaves in a very nice manner with respect to the rank of the rank function of the hypergraph. So let me explain what I'm going to talk about today. So the first thing is what I said, which is extending the Tutte polynomial from the setting of graphs, where it is well known. Actually, usually what is well known is that this is an invariant of graphs and more generally matroids. And we want to extend that to this more general setting of hypergraph and more generally polymatroids. So that's the first part. And then in the second part of the talk, I'm going to talk about what we call the universal Tutte polynomial, which is a way of parametrizing the Tutte polynomials of every polymatroid in terms of the rank function. So Z is going to be variables that if we plug in the rank function, then you get the Tutte polynomial of the corresponding polymatroid. So in that setting of polymatroids, things become a little bit more geometric in flavor. And this universal Tutte polynomial is going to be a Ehrhart type polynomial. So it's kind of counting points in polytopes. But yes, but in many variables. Okay. All right. So that's the outline. Let me jump and record the the basis, which is about the Tutte polynomial of graphs. Okay, so what is the Tutte polynomial of a graph? Let me take a graph G. Its Tutte polynomial, Tg, is a polynomial in two variables, which are counting the subgraph. So I'm looking at subgraph as subset of edges here. And I'm counting this subgraph according to two parameters, the corank and the nullity. The corank of a subgraph is the number of edges you need to add to that subgraph in order to get a connected subgraph. So it tells you how much disconnected you are. The nullity is number of edges that you need to delete in order to get an acyclic subgraph. So this is a measure of how many cycles you have. Okay, so you count your graphs according to these two parameters. And okay, let's do an example. For instance, I take this graph. I look at all the 2 to the 5 subgraph of G. So for instance, this is one of them. For each of these subgraph, I'm going to look at the corank and nullity. So for instance, here the corank is 1 because I need to add one edge to become connected. And the nullity is 1 because I need to delete one edge in order to get to be acyclic. So this subgraph here is going to contribute x minus 1, y minus 1 to my sum. I sum everything, and you see it could look much more, much bigger than that, but it's a nice expression at the end, this polynomial. Okay, the reason to be interested in. Okay, so let me pause now for questions. Anyone want to ask a question about this definition? All good so far? Okay, so the reason the Tutte polynomial is well known and well studied is that it captures a lot of enumerative information about the graph. So for instance, from the definition, it's not hard to see that you can get the number of spanning trees, forests, connected subgraphs. But maybe more surprisingly, you have a lot of other enumerative information about orientations, for instance, cyclic orientation, totally cyclic orientations, or about colorings, like the chromatic or Potts polynomial, or SunPy model things, or reliability polynomial. So this contains a lot of information. One way to understand it contains a lot of information is it's so-called universal, meaning it contains all the invariants of graphs that have a linear recurrence relation in terms of deletion and contraction. Okay. All right, so that's the motivation for studying this invariant. So now let me tell you one more thing about this invariant, which is another definition of the polynomial, but in terms of internal and external activities. Okay, so for that, so I'm going to give a new formula for the Tutte polynomial, but for that one, I need to fix a total order on my edges. Once I fix that, I can define for a spanning tree T two sets, the internal active edges and the external active edges. Okay, so the internal active edges, that's the edges in the tree, which cannot be replaced by a smaller edge, meaning there is no edge E prime less than E, such that if I, delete E and replace it by E prime, I'm getting a tree. Okay, so in that case, I say that E is active, internally active. For externally, it's the dual, it's externally active if it cannot replace a smaller edges of the tree. So it's an edge that is not in the tree but that cannot replace a smaller edge in the tree. So let's do an example. Here are my 5 edges that I have ordered in this matter. This is 1, 2, 3. So this is the smallest, and then 2, and then 3, and 4, and 5. Which one are the active edges? So the edges of the tree that are active is just 1. Of course, 1 cannot be replaced by a smaller edge. So 1 is always active. But the other edges are not active. So for instance, 4 could be replaced by a smaller edge, namely 3. Okay. And for the edges, the external edges, the one that are the only one that is active is 3. 3 cannot be replaced cannot replace a smaller edge. It could replace either 4 or 5, but it cannot replace a smaller edge. So that's your set of internally active edges and externally active edges in this case. Okay, and the result is that the Tutte polynomial is actually the generating function of activities of spanning trees. So you get the Tutte polynomial by summing over all spanning trees, x to the number of internally active edge, y to the number of externally active edges. So that's a nice result, but it's kind of surprising because the definition of these sets of this activity definition, they depend on this linear order that we fixed at the beginning. So the contribution of a given spanning tree is going to depend on that, on that order. However, if you sum over all trees, the result is independent of that order. So there is this kind of miracle occurring here. So let's take just an example for this theorem. Here are the 8 spanning trees of my graph. And for each of them, I have indicated which edges are active and therefore their contribution in this sum. Okay, so for instance, here there are 3 internal active edges. So I get a contribution of x3. I'm summing them all, and I get this expression for the Tutte polynomial. Okay. Any questions so far? Okay, so the natural question is why these two relations these two expressions coincide. So I have two names here because actually Tutte started with this definition of the Tutte polynomial, and it's only later that a more explicit definition in terms of subgraph was found. So what Tutte did is to show that this is invariant, but kind of in an ugly way. But later on, the relation between the two expressions was understood. So the way it works is that, okay, so I'm going to do the example on this graph G. And the relation is that is this interval partition that is due to Crapo. What is it about? So I'm looking at each spanning tree of the graph. Here I have 3 spanning trees. And then for each spanning tree, I'm going to associate a bunch of subgraphs, namely all the subgraphs that I can obtain from my spanning tree by flipping the active edges. So here, for instance, I have the active edges that are 1 and 2. So I can flip them, meaning I can delete them if I want. Okay, so I have these 4 subgraphs that I get in this manner. Here, the active edges is just 1, so I get these 2 subgraphs by flipping. And here, this edge is the edge that is active, so I get these 2 graphs by flipping it. Okay, so the point is here that this forms a partition of the set of all subgraphs. So the activities encode these intervals in the Boolean lattice of subgraphs, and these intervals they partition the full set of subgraphs, the full lattice of subgraphs, and through this correspondence between spanning trees and intervals of subgraphs, the contribution coincide. So for instance, this tree contributes x squared to the Tutte polynomial, and so does this this sum of subgraph if we take the definition in terms of subgraphs. Okay. All right, so that's the relations. I'm not justifying this this fact here. These two points: the fact that this is a partition and the fact that the contribution coincide. But that's what's underneath the correspondence between these two expressions. Okay, so now I want to move up my ladder of generalizations. So first, let me recall what's happened for matroids. So matroids, if you are not familiar already, matroids are abstractions of a graph. And one way to think about matroids is I'm not going to tell you what are the vertices. You will have your set of edges, and what I'm going to tell you which subset of edges form a spanning tree. Okay, that will be the only information that I'm going to tell you about the graph. Okay, so precisely, a matroid on a set E is a set of subsets of E, whose elements I'm going to call bases, which satisfies this property, the exchange axiom. So what's the property? It says that if I have 2 bases, A and B, and an element I, which is in A but not in B, and an element J, sorry, let me restart. If I have an element I, which is in A and not in B, then there exists an element J that is in B but not in A, such that I can replace I by J in A, and I can replace J by I in B, and still obtain bases. Okay, so that's the exchange axiom. If my set of subsets satisfy this exchange axiom, I call that a matroid. So I was saying this is an abstraction of okay, so let me give you an example here. Let me take the set of edges to be the set 1, 2, 3 4, 5. And let me take M be this set of subsets. Then you can check that this set of subsets satisfy the exchange axiom. If you take any two bases, you will see that you will be able to exchange an element from B from an element of A. And therefore this forms a matroid. The way you should think about this is as this set M should be thought as the set of spanning tree of a graph. So the statement is that for any connected graph G, the set of spanning trees is a matroid on E. Okay, so in other words, this set of spanning trees, they satisfy this exchange axiom. If you take two spanning trees and an edge that is in one and not in the other, you can make an exchange and get two new spanning trees. Okay, so for instance, the earlier matroid that I was presenting correspond to that graph. Here, this set of subset is the set of spanning tree of that graph. Okay, all right. So so of course, if you are familiar with matroid, here I'm going to identify the matroid with this set of bases, as you can see. Okay. Okay, so I want to define the Tutte polynomial to matroids. The definition, the classical definition is as follows. You take the sum over all subset of edges according to two parameters, the corank and nullity, which are defined as follows. The corank of a subset is the number of elements that you need to add in order to get something that contains a basis. And the nullity is the number of elements you need to delete in order to get a subgraph that is contained in a basis. Okay. And there is also the equivalent of the activity this definition for the Tutte polynomial, which is the natural generalization here. The Tutte polynomial is equal to the sum over all bases, x to the number of internal active edges, y to the number of external active edges, where the internal and external active edges are defined in this manner. So an edge is of the basis is active if it cannot be replaced by a smaller edge. An edge outside of the basis is active if it cannot replace a smaller edge. Okay. All right, so that's all the classical theory. Now I want to move to this new field here, where I'm going to talk about hypergraphs and polymatroids. So I'm assuming that you are not familiar with this concept. So I'm going to first discuss what polymatroids are. So roughly speaking, it's a relaxation of matroids. Instead of matroids, we can think of, if I'm thinking of the basis as, if I'm thinking of each basis as a 0, 1 vector, if I identify a basis with a subset of 1 to n as a 0, 1 vector, I can think of my set of bases as a subset of 0, 1 to the n. And now I'm going to move, instead of going to work in this space, 0, 1 to the n, I'm going to be working in z to the n. Okay, so that's the idea of this generalization. So I'm going to use the following notation. I'm going to denote by E1, E2, En the canonical basis of z to the n. So you know EI is the vector that is 0, 0, 0, 1, 0, 0, 0, 0. And when I have an element A in Z to the n, I'm going to denote by AI its coordinates. Okay, so what is a polymatroid? So a polymatroid on a set E, and my set E is going to be 1 to n. For convenience, so a polymatroid on 1 to n is a finite set of Z to the n, which satisfy the exchange axiom. Okay, so what's the exchange axiom? It says that if I have two elements of my polymatroids, A and B, and the ith coordinate of A is bigger than the ith coordinate of B, then there exists a J such that the J's coordinate of B is greater than the J's coordinate of A, and I can increase the J's coordinate of A by 1, decrease the ith coordinate by 1, and stay in P. And dually for B, I'm increasing the ith coordinate, decreasing the J's coordinate. I'm staying in P. Okay. So that's the exchange axiom that define polymatroids. So here is an example of a polymatroid on the set 1 to 3. So, well, it's clear from the definition that all the points, have, the sum of the coordinates is constant over the polymatroid. So here the sum of coordinates is 4 for this particular polymatroid. And here are the points in my polymatroid. You can check, so each one is what I call a basis. And then you can check that, for any two bases, I have this property. It satisfies the exchange axiom. So this is a.
I'm sorry.
Yes?
Does it follow that they all have the same sum of coordinates, or is it required that they have the same?
No, it follows. Okay, just from the first line, if the ith coordinate is greater than A, then there exists a J in which B is greater. So this let's say it's not hard to prove from this exchange axiom.
Thanks.
What happens here, if you see A and B, you can get closer to one another in some direction. So there is a path from A to B that is for which it's constant. The sum of coordinates is constant. So it implies that everyone in the polymatroid has the same sum of coordinates. Yeah. Any other question about this? No. All right. So okay. So now what's the relation with matroids? Okay. So it looks a little bit the same. This exchange axiom. So if you have a matroid M, and you look at the corresponding, you look at this matroid M. Remember that this is the set of bases, and you look at this each basis as a point, namely the 0, 1 vector that correspond to each basis. So here for a basis of my matroid, I'm going to associate the point which is 1 for each edge it takes, and 0 for the edges it doesn't take. So that's also known as the base polytop of my matroid. This base polytop is a polymatroid. In fact, it's easy to see that this exchange axiom corresponds to the exchange axiom for matroids if we restrict our attention to polymatroids contained in 0, 1 to the n. Okay. All right, so that's the definition of polymatroids. As I said, one of the main motivation for polymatroids are hypergraphs. So let's see how hypergraphs can be seen as giving polymatroids. So let me define a hypergraph on a set V as a multiset E of subset of V. So the elements here in E are, the hyper edges. So, they contain a certain subset of vertices. Okay, so this hyper edge here contains this vertex, and this vertex. That's what this picture represents. Okay, so that's a hypergraph. And of course, this is a generalization of graphs. If we restrict our attention to hypergraphs where every hyperedge has degree 2, contains 2 elements, that's going to be, a graph. Okay, so now I have this generalization of graph. I want to have a generalization of spanning tree. So what should be, the analog of spanning trees, but for hypergraphs? So I want this, to coincide for the, the base case of graphs. Okay, so I want a definition that is going to work well for graphs. So let me give the definition of a spanning hypertree. So let H be my hypergraph, and let me denote by BH the corresponding bipartite graph. So in that's BH here. That's the bipartite graph corresponding to my hypergraph H. So I'm going to call a spanning tree, a spanning hypertree of my hypergraph will be a function from the set of edges to the non-negative integers, such that this function corresponds to the degrees of a spanning tree of the bipartite graph BH. Okay, so precisely delta is a spanning hypertree if there exists a spanning tree of the bipartite graph such that the value of delta on every edge, on every hyper edge, is the degree of the tree at that hyper edge -1. There is a little shift here. Let me give it an example. Let me take H. So this is the bipartite graph corresponding to my hypergraph H. And what are the function deltas? The function deltas are either 2 for this hyperedge and 0 for this one, or 1, 1, or 0, 2. So for each of them, I have representing a spanning tree that represent that spanning hypertree. So for instance, here, if you look at this spanning tree of the bipartite graph, the degree here is 3, and the degree is 1. So the delta is 2 and 0. So that's that delta is a spanning hypertree. That delta is a spanning hypertree. That delta is a spanning hypertree, and there is no other spanning hypertree. Okay. Any question here? So, okay. So in other words, you see there's the subtlety here is that we are not going to look directly at the spanning trees of the bipartite graph. What we'll do instead is only abstract the degree of that spanning tree. So in other words, we are looking at for every hyperedge, we'll look at how many connections does it create. Okay, so here, let's say it creates 2 connections here and 0 connection here. Or this one, it connects it creates 1 connection here and 1 connection here. That's the spanning hypertree. So for instance, if I take a hypergraph that corresponds to a graph G, then I'm claiming the spanning hypertree of H are in bijection with the spanning trees of G. Okay, so let's look at that. So I'm looking at this graph G, and this is my corresponding hypergraph, or that I represent as a bipartite graph here. Okay, so these are the hyper edges. And if I have a spanning tree of G here, this edge creates a connection. Here, this edge creates a connection. This edge creates a connection. So now, if I look at the bipartite version here, I have added one, one vertex in the middle of each edge. So I need to complete, my spanning tree by, by connecting these middle vertices in somehow. But we'll have, edges that have degree 2 and edges that have degree 0. The edges that have the hyper edges that have degree 2, they are the one that create the connections, and the one that have degree 0, they don't create any connection. Okay. So in other words, the connection, the correspondence between the spanning trees of G and the hypertree and the spanning hypertrees of H is very simple. Each time that you have an edge of the spanning tree, you get 1 for delta. And if you don't have an edge in the spanning tree, then you have 0 for delta. So in this manner, you have a one-to-one correspondence between spanning trees of G and spanning hypertrees of H. Does that make sense? Okay, so that's the generalization of spanning trees. So accordingly, for a hypergraph H, I'm going to look at the set of spanning hypertrees. And so for instance, for this example, I had 3 hypertrees, 2, 0, 1, 1, and 0, 2, which correspond to 3 points here. And this set of points here form a polymatroid on the set E. Okay, so that's the claim. So for a graph, the set of spanning tree form a matroid. For a hypergraph, the set of hypertrees create a polymatroids. So this is the the main motivation for polymatroids from a combinatorial perspective. They are the generalization. They correspond to polymatroids are for hypertrees what matroids are for. Sorry, the polymatroids are for hypergraphs what the matroids are for graphs. Okay.
Is that easy to say which polymatroids come from hypergraphs? Is that Minkowski sums of simplices or something like this?
Good question. There is a characterization. Okay, so there is a characterization. Indeed, there is a certain positivity involved. But okay, I'm going to pass on this question because this would be complicated to answer, and I think I'm going to yeah, this would kind of lead us outside of the main focus. But let me say, however, that the hypertrees, the polymatroids that come for hypergraph, they are abundant in the sense that they form a subset of the right dimension. Okay, so it's not really like in the case of matroids, like the graphs are very special types of matroids. For polymatroids, the hypergraphs, they form a class that is special, but but general enough that it has the right dimension in the cone of cone of generalization of parametrization. I'm going to talk about that a little bit later. In particular, when you want to prove something about general polymatroids, if you have something that is polynomial, it's sufficient to prove it for hypergraphs. So that's a nice property too. Okay. And yeah, you are close to the mark. I mean, if you do Markov sums of the right simplices, you are a hypergraph. There is a little bit more because you can subtract a little bit. So okay, anyway, let me pass on that. Okay, so at this point, I have these generalizations of graphs and matroids. I want to define the Tutte polynomial for those. So this is the original motivation. How do we define the Tutte polynomial of a hypergraph? So what we'll do here is we have this generalization of spanning trees. So we can work with that. So what we want to say is, let's take a polymatroid P. And for each element of P, I'm going to look at two sets, the set of internally active elements and the set of externally active elements. Okay, so same idea as before, so we're going to say that an element I is internally active for the basis A. If I cannot decrease the ith, I cannot compensate the decrease in the ith coordinate by an increase in a smaller coordinate J. And I'm going to say that an element is externally active if I cannot decrease the J's coordinate and compensate by increasing I cannot decrease the J's coordinate and compensate by increasing cannot increase the ith coordinate and compensate by decreasing a smaller coordinate J. So that's that's kind of an analog of activities here. And let's try defining the Tutte polynomial in this manner as this generating function of bases counted according to the internal and external activities. Okay, so that's a reasonable definition, but it doesn't work because it doesn't have the one of the essential property, which is that it should not depend on the order. The order is kind of irrelevant here, and whereas we had this miracle for the Tutte polynomial that this sum did not depend on the order, here, if you take this definition, it does depend on the order, so it's not nice. So it's not an invariant of your polymatroids. However, as was noticed earlier, the specialization, when you specialize one of the variables to one, then these are invariant under reordering, which suggests that it's close to be correct, but it's not. And the trick is simply to do the following. So there are elements here that are going to be both internally and externally active. And instead of them contributing x, y, I'm going to have them contribute x plus y minus 1. So now I'm going to sum over all bases, x to the number of elements that are internally active but not externally active, y to the number of elements that are externally active but not internally active, and x plus y minus 1 to the number of element and the indices that are both internally and externally active. So, well, if you do that, so for instance, here for this polymatroid that I shown earlier, this is the result you get. So for instance, if I look at the contribution of that point, I would wonder what are the internally active elements. So one is always active. And two is also active. That's because if I go in this direction, if I try to replace 2 by 1, I cannot replace 2 by 1. So it means that 2 is internally active, and all 3 indices are externally active. So for instance, it's externally 2 is externally active because I cannot replace 3 by 2, and for 3 I need to check that both of these do not work. Okay, so I would have this contribution for that point, and then I sum everything, I get this. So that's the Tutte polynomial for polymatroids. And this polynomial is indeed invariant under reordering of n. So it is a proper invariant which generalizes the Tutte polynomial. So you have to make a change of variables here because actually, although this definition looks similar, it's not exactly the same as the one we have before, because now we are considering more things to be active than before. So if you make your computation for matroid M, the Tutte polynomial of M and this new invariant applied to the polymatroid of M, they coincide, but up to a change of variable.
I'm sorry, why is this not obvious that you just recovered the Tutte polynomial for matroids or for graphs, let's say?
Yeah, so the main difference, okay, apart from this, thing that is looks different, the main difference is here is that the edges, that are in your tree, for instance, they would be considered automatically externally active, and some of them are internally active as well. So because you can if you are inside the tree, and then you can not add that to the tree and get a tree. So okay, so that's why actually in this definition the edges in the tree are automatically externally active, and the edges outside of the tree are automatically internally active.
Okay.
So you have this change, but this is just a change of a variable because we have a slight change of definition of what we consider active.
Okay.
But yeah, but the essential part of the definition remain the same, so you can make the change of variable.
Okay. A quick question. So
yes.
Your previous definition, you said that so you don't get the polynomial being invariant. Do you get a lot of different polynomials coming out of it, or is there sort of a small number of different ones you get under the different orderings?
Well, I don't know. It's hard to quantify. I mean, actually, for polymatroids that are well behaved, that correspond to simple polytopes, then you actually have an invariance. So the invariance is put to default when you get closer to the matroids case, where you have a lot of singularities in some sense.
Okay, thank you.
All right. So then there is this question of having a definition that does not require to look at this particular order, which is arbitrary, and understanding in this manner the invariance. So we are going to I'm going to present a kind of an analog of the interval partition, but this time I'm going to partition z to the n instead of 0, 1 to the n. So for an element A in my polymatroid, I'm going to define a cone, which is defined starting from the basis by allowing to grow in various directions. So I'm going to allow to grow either by half line down or a half line up, or along the full line according to whether I'm internally active but not externally active, or these other situations. So let me give you an example that's going to be clearer. So here is the polymatroids that I had in R3. So for instance, this one here, you know, the coordinates 1 and 2 were internally and externally active. So I'm going to be able to I'm going to extend in both of these directions, the one direction and the two direction, and instinctively. And also for 3, it was externally active, so I can increase in the 3 direction, but only up. So I'm going to get this, you know, half space here corresponding to that point. And here, for instance, for the other, I could get, you know, a half plane or line for this one, or, you know, a quadrant or something like that. Actually, they all contain the line in the direction 1, because 1 is always, you know, internally and externally active. So if you project here, you along the lines that they all contain, the partition look like this. Okay. The claim is that this is a proper partition of z to the n, and now I can get the polymatroid Tutte polynomial as a sum over all the elements of Zn, where I count these points according to 2 parameters: the number of things, the number of increase I need to do to my coordinates to be above an element of my polymatroid, and the number of decrease of coordinates I need to do in order to be below, oh sorry, this should be an A, to be below an element of the polymatroid. Okay, so this is a kind of a generalization of the corank-nullity. Okay. But to the z to the n lattice. And that's why, because you have this partition and the contribution, so the reason you get this, this correspondence with this new characterization is that, as before, you know, the conc associated to an element A is going to, their contribution here is going to sum to the contribution of A up to that change of variable. So that gives you a new characterization, a new definition of the Tutte polynomial, and this one is clearly invariant by permuting the coordinates. Okay, so lastly, let me say one more thing here, which is this invariant is related to the Cameron and Fink invariant that was introduced earlier in terms of a Herhardt polynomial type of invariant. Namely, the definition was as follows. You look at your polymatroid and you look at taking a Minkowski sum of this polymatroid with the simplex and the inverted simplex. And you look at the number of points in this Minkowski sum, and that gives you a certain polynomial. Okay, so this is a Herhardt type polynomial that counts the number of points in this Minkowski sum. And then the correspondence is that the coefficients of our polynomial and the polynomial of Cameron and Fink are the same up to this change of basis of polynomial. So the polynomial in the polynomial here is in the factorial basis and in the monomial basis here. Okay, so now I'm in this second part of the talk, although we are close to the end, so I'm going to go fast. So the point is, now we have this polynomial which is associated to a polymatroid. So let's look a little bit at this from a geometrical point of view. So I'm going to call generalized permutahedron a polytop such that every edge has direction of the form ei minus ej for some ij. And the relation is that a polymatroid in Zn is so the polymatroids in Zn are the lattice points of generalized permutation. So P is a polymatroid if and only if P is the set of lattice points of a generalized permutation with integer vertices. And okay, that's the geometric part. So I'm looking at this type of polytopes. And I want to parameterize this polytope. So I'm going to look at the rank function. So a definition here, a function from the set of subset of 1 to n on to R is submodular if f of the empty set is 0 and it satisfies this inequality for any subset AB. And the proposition is that a submodular function gives rise to a polymatroid. If I look at the set of points, so if I fix a submodular function f, and I look at the set of points in Zn whose facets are given by the value of this of the submodular function, this is going to be a polymatroid. Okay, so precisely I want the sum of coordinates to be equal to f of the set 1 to n, and for any other subset I want an inequality. So the sum of coordinates ai is to be at most f of I. So here is the picture. F of 1 to 3 is going to tell you, the plane in which you are, and then f of each set is going to tell you, the position of each of the facets. So this is your rank function. In fact, for any polymatroid, there exists a unique submodular function f such that P is given by this inequality Pf. So f is called the rank function of the polymatroid. And the conclusion is that there is a way of parametrizing the set of polymatroids by submodular functions. So in other words, we are looking at, submodular functions. But what are submodular functions? They are lattice points in the following polyhedron of dimension 2 to the n minus 1. The cone that correspond to all of these inequalities and equality. Okay. And the properties that we proved is that the Tutte polynomial of polymatroid is polynomial in the rank function. So let me give that in a more precise manner. There exists a unique polynomial, Tn, such that for all submodular function f, the Tutte polynomial of the polymatroid with rank function f is the evaluation of Tn by replacing the variable zi by f of I. Okay, so this polynomial Tn has the two variables xy plus one variable zi for each subset I in 1 to n. And when I specialize these variables to the rank function, I get the Tutte polynomial of the polymatroid. So this is the example for T3. And you see this is a polynomial expression in Z. So a polynomial expression in the rank function of the polymatroid. So I'm going, I think this is time for me to stop. So I'm going to stop there and saying that this is the universal Tutte polynomial that parameterize all the Tutte polynomials on the edge set 1 to n. So let me stop and say thank you.